Let me pay the bibliographer. Let's see. We were talking about how the application of the conditions on the fields transformed properly under translations, boosts, and rotations allowed us to determine what the actual spinners were. We did this for spin 0 and got derived the fact that spin 0 fields have to obey commutation, not anti-commutation relations, which is part of a general theorem called the spin statistics theorem, which says that integral spin fields are bosons, half integral spin fields are fermions. Okay. Now, this is a matter of conserved charges, and in fact, one of the physical laws, one of the conservation laws that's most accurately how shall I say, observed and verified technically is conservation of charge. The precision on that is many decimal places. I don't remember how many, but I remember being amazed when somebody told me what the number was. The way, as you know, the way I think of it is we actually have, in the simplest case of spin 0, we have two fields of the same mass. And we make a new field like this, phi 1 of x plus I phi 2 of x. And so this is an integral dq(p) over 2 pi cubed 2p0, 1 over root 2, then it's a1 of p plus I a2 of p e to the I px plus 1 over root 2, a1 dagger of p plus I a2 dagger of p e to the minus I px. And we can rewrite this by saying that this is equal to a of p and the second one is not a dagger because it would have a minus sign, so we'll call that b dagger of p. And of course, this implies that b is the adjoint of that, so in particular, b of p is 1 over root 2, a1 of p minus I, a2 of p. And this trick of going from two Hermitian fields of the same mass to a complex field in which you have annihilation operators for particles and annihilation operators for antiparticles. This is very, very general. And so now the field can be written as an integral dq(p) over square root of 2 pi cubed 2p0, and so that's a of p e to the I px plus b dagger of p e to the minus I px. And phi dagger then is the adjoint of that. The commutation relations of these are A of P, a dagger of P is, well, let's see, why did I put spin in there? Where's spin 0? Let me fix it. So this is simply delta cubed of P minus P prime. And B of P, B dagger of P prime is delta cubed P minus P prime factor. Let me just assign a really simple homework problem. Derive these commutation relations as well as the commutation relation A of P, and or let's see, I don't say that. Also, derive the commutation relations for A of P with B of P and A of P with B dagger of P and so forth. So derive, given the commutation relations, these are spin 0 commutation relations, for A1 and A2, and these definitions derive the commutation relations for the complex annihilation and creation operators. Yes, Sam?
So, I don't know, you're calling these B's like creation annihilation operators for antiparticles. Is there a reason why? Are we going to see that later? Why that's natural to call them that? Or because you just kind of said that, and then
the name,
you said they're B's, or does the name just not matter? Or, I don't know.
Well, what we'll find is that if fields, there are all kinds of fields that are, well, the generic physical field is charged, right? All the quarks are charged, the leptons are charged apart from the neutrinos. And so what happens when you couple fields like this to the electromagnetic field, let me just say what the coupling is. The coupling is essentially, if I use the conventional picture, it's A mu psi bar d mu psi. If psi is the, say, the Dirac field. If we're talking instead spin 0, then it's a similar coupling. It's A mu phi dagger d mu phi, where this is the complex field. Okay?
This is the coupling of what?
This is the electromagnetic field.
Okay. Yeah, but it's the coupling of what, particles to antiparticles? Is what you're saying?
Well, all right, let me expand this and we'll see.
Mm-hmm.
So this is A mu phi dagger. So phi dagger, you see, will have you'll have things like d cubed p over the square root. You will have a dagger of p e to the minus I px plus b of p e to the I px. And then you'll have a derivative acting on the other one, d cubed, say p prime over, I'll just leave out, I mean the square root is the same square root as this square root. And this will be a derivative acting on these, and so this will be a of p prime e to the I px, and then b dagger of p prime e to the minus I px. And now when the derivative acts, you're going to get this is a derivative with respect to the lower one, so you're going to have the upper one. So this is I p mu minus I p mu. So that's what this is going to look like. All right? Now this A, to anticipate something, this A mu is going to be again some integral d cubed k over again x square root, and you're going to have, well, polarization vector E mu, and then you're going to have A of k dvi kx plus, in general, and this actually will have an index in it for polarization. So that's what the interaction looks like. All right. Now, these are all creation and annihilation operators, and this structure here is part of the Hamiltonian, part of the interaction. The interaction density, which, in other words, part of the interaction Hamiltonian in this, in the, if we want, all of them are at x. So this is the interaction Hamiltonian density is A mu psi bar du psi, or in this case, it's, so let me go from Dirac back to what we're doing here. Phi dagger d mu phi, where phi is a complex field. So, in particular, if you have simply h of x occurring between some initial state and some final state, that's not actually going to cut it because you're not going to conserve Lorentz, conserve Hall momentum. But if you have two of these and you integrate d4 of x prime, like that, that would be a term in the expansion of the time-ordered exponential e to the minus I integral h of x d4 of x from some initial state to some final state. So this is part of the S matrix. And when you expand this to second order, you get terms like that. All right, now how does this look? Well, suppose you have an initial state here that contains an A particle and a B particle, which we're interpreting as a particle and an antiparticle. What can happen? Well, what can happen is that you can have a non-zero probability of the final state being 2 photons. And the way this happens is, in this interaction Hamiltonian, let me draw the Feynman diagram just to make things easier for myself. What it'll look like is actually this. And so what will happen here is that at one vertex, you have one of these h's, and that's one of these terms. And what will happen is the annihilation operator here will annihilate. So this will have one annihilation operator, say A of p prime, from here. And then that's multiplied by an A. This A has a creation operator for a photon, so we'll have A dagger of K and S. So I'm basically cherry picking the product of these things is a lot of terms, because I guess for each H you have 6 terms essentially. You have 2 from here, 8 terms, times 2 from there, times 2 from there. So you have 8 terms there, times 8 terms. You've got 64 different terms. I'm cherry picking them to show you the one that looks like, that makes you think of antiparticles. Oh, unfortunately I have used an A for the annihilation operator of the photon, and A for the annihilation operator for the charged spin zero boson. So let me call this C for the photon creation and annihilation operators. So this will be a creation operator for a photon, and so I'm taking those two out. But then there's another thing here, namely, we've got, I can either use the B term, so in other words, I used A here. I could use B here, but I'm not going to use B here. I'm going to use an A dagger. So I'm going to have an A dagger of P now. And then in the second term, I'm going to use an A of P prime. And then this is I've gotten things backwards. I'm going to use, all right, sorry, I screwed up this a little bit. So I'm going to use an A and a C dagger. And so I've used one from here, one from there, and then the extra one is going to be, let us say, an A dagger, because that's the other term there. So I've used one from here, and one from there, right? Well, wait a second. I've got two of these. Hold on a second. So, from this one, I'm using an A. From this one, I'm using a C dagger. And then from that one, I'm using an A dagger. Okay. Now, for the second term, I'm again going to use an A, which will annihilate this guy, so P triple prime, from here. And then from this guy, I'm going to use a B, which annihilates the B particle. And then from the photon field, I'm going to use again a creation operator. So altogether, this is a situation where the charged particles annihilated here produces a first photon. So this is this one. This operator produces that line in the Feynman diagram. Then this operator and that operator together produce this line in the Feynman diagram. Then the B annihilates the incoming antiparticle. And so this is this line. And then the C dagger is the outgoing photon. And that looks like that. So this is why we call these antiparticles. In other words, if you have an initial state of an A and a B, you can produce two photons in the final state. And a common example of this is I guess if you produce positrons and they just hit anything, they annihilate with the electrons in the material that they hit. And so that's E plus, E minus goes to two photons. And these are half an MeV. If they're not moving very fast, the two photons that go out are half an MeV photons. Another possibility is just pi zero decay. Pi zero can go to 2 gammas in around 10 to the minus 16 seconds. And the pi zero is basically an up and an anti-up claw, or a down and a down. It's a linear combination of UU bar, DD bar of different colors. All right, we've got, let's see, you asked a question and never got candy, right?
Yeah.
All right, and, all right, I'll pay in advance.
It's gonna look great.
Is the camera still okay?
Yeah, it's fine.
Did you get one? Just-
Oh yeah, you just gave me one.
All right, so all right, so I don't know who went first. What's your question?
Yeah, I was gonna ask if you could describe again what all these terms were and like what these different terms in the Feynman diagram mean. I was also wondering like is there like a direction that time is going in this? I guess time is
All
going up, but what is like?
All right, all right. Most
I don't know.
people draw Feynman diagrams with time going that way or that way.
Okay.
Weinberg draws time going this way.
Okay.
And I've grown to like that a little better, but
Yeah,
so that's that. Then what we've got as this H is A mu phi dagger D mu phi. Notice this is Lorentz invariant because you've got a derivative and a covariant field. These being scalar fields. So then so then the product of those three, this is H. H of x then is equal to that. So it's the A mu, which is this, times a phi dagger, and this is the derivative of phi. Okay? Now, when you have them between an initial state of a particle and an antiparticle of each of a particular momentum, and then you have a state of two photons, each of a particular momentum in the final state, you can pick out of this product of 2 times 2 times 2, or eight terms, 8 different terms in h of x, and another 8 in h of x prime. You've got 64 terms. You can cherry pick them to find combinations of, this is basically one annihilation operator. This is one antiparticle annihilation operator. And this is a photon creation operator and a photon creation operator.
Then what's the significance of the term in the middle? The AA dagger?
This thing,
Yeah, what is that like doing?
well, that's the fermion propagator is what it's actually called. But the point is that when you cherry pick these terms, you see you have, here are the C daggers for the final state photons. These are the annihilation operators for the initial state particle and antiparticle. But then you've got these, you've got to have a product, you see, of 6 operators. And so you've got 1, 2, 3, 4. You need 2 more, which would occur in any product of h times h of x times h of x prime. H of x times h of x prime is a linear combination of 64 terms, each term being a product of 6 operators, 6 creation and annihilation operators. And one way...
But you just didn't want the A. You didn't want the A to come first because otherwise the
well,
matrix element would be 0.
Well,
so
yeah.
A dagger. If it was A dagger A, you'd be screwed. If it was AA, you'd be screwed. If it was A dagger, what about A dagger, Well, I'm thinking.
The A dagger, the final state here is gamma gamma, 2 photons. This creates a photon, that creates a photon.
Okay.
That turns that into the vacuum. This one times this one.
Sure. I see.
Oh, wait. Yeah, no. This one times this one turns this into the vacuum. Vacuum times vacuum is unity, so that's non-zero. And this is part of the propagator. Another part of the propagator. So there are 2 ways to cherry pick this thing.
So you're only picking out ones that produce the 2 photons, like you're.
Yeah,
there's
I'm
something like,
only looking for terms that produce this. there is another,
I'm sorry.
Is it possible to create one A first and then another?
yes, that's what I was about to write down. Here, let me just, good catch. All right, let's cherry pick another term. All right, now let me try to get this right. I mean, one thing is we could have started with a B here, with a we could have started with a B term here. Okay, so we would have taken a B from that one. And then we can still go with the C dagger of K and S. But now we have to take one from here. And now we would take, let's see, could we choose this? I don't think so. You see, if we chose this one, we would then be back to the vacuum state. And we then have the problem that we would be, we could get a non-zero amplitude, but it would be for a different process. So what we do then is we pick, say, a B from here, a C dagger from there, and now from this one we're going to pick a B dagger. And so then, from the second vertex, we're going to pick a B to annihilate that B dagger because we only want one antiparticle. We can't annihilate a second antiparticle. Then we pick an A from there and a C dagger, gamma gamma. So this is another possibility. This is what you were thinking of, presumably.
No, I think he was thinking A dagger and then a double A. So you create an extra charged particle, and then you delete the two. I don't know, does that, or maybe it just doesn't make sense physically?
Okay, so you wanted to have, where did you want to create the, see in both cases we created a new particle, and then annihilated it, and then annihilated the initial one. All right, so I guess another possibility is in the very first term we could have picked, say, a B dagger from this one, and then from the other one we could have picked. All right, which one did you want? Is this? Yeah.
Oh. I don't know, do you want to finish answering somehow?
All right, let's go with yours. What were you thinking of?
Let's have a B dagger first and then two B.
B dagger first and then?
Two.
So that's one from here. What do you pick from there?
A B.
A B. Okay, and then we have a C dagger, say. And then now you have a second vertex, and you've still got two particles. Yeah, this won't work. Well, maybe it will work. Let's see. Yeah, I think you're right. This also works because in this from the second. So all this is from the first vertex. You just pick a B dagger from here and a B from there, and a C dagger from there. Now from the second vertex, we have to annihilate both incoming particles, so we pick an A from there, a B from there, and a C dagger. Right, okay, so you're right. That's another possibility. And we can sort of infer from that that we would also possibly have A dagger A, and then BA, or one could presumably have that as well. So there are various processes that could could give rise to an amplitude for particle antiparticle goes to 2 photons. Yes.
So is every term in this kind of linear combination, or can you identify with the physical process that happens?
Well, it's a possible.
Okay.
Every diagram. So let's just say see how many there are. There are 64. There are 64 terms in second order. Depending on what the initial and final states are, many of them are 0, and in fact most of them turn out to be 0 if you have 2 particle initial state, 2 particle final state. Most of them are 0 just because the momenta are wrong. But you're integrating over momentum, so you always catch the appropriate spin and momentum because you sum over spin, integrate over momentum. But many of them, you know, are ones where, I mean, you could have picked 2 creation operators from the first vertex and 2 creation operators from the second vertex, and then that would have given you a process where you had 2 particles in and 6 particles out, just counting fermions, and then you could do what you want with the photons. You could have 1 in, 1 out, 2 in, 2 out, whatever you want. And so all these are essentially, I guess, possible amplitudes. But then when you integrate over space twice, you get a 4-dimensional delta function that conserves energy momentum twice.
So if you have like 2 fermions going in and 6 coming out, doesn't that violate like lepton number or something?
Well, I mean, it depends. This can be a particle, antiparticle.
Oh,
these are spin 0 bosons, but anyway. What happens is the structure of the interaction will automatically, and the nature of this mathematical procedure here, the integration over space conserves energy and momentum. The structure of the Hamiltonian conserves the various charges that you want to conserve. Yes?
I was going to ask this last one that you wrote here, the A dagger, A, C dagger, A, B, C dagger, on the very bottom. How do you get the A dagger to come first? I don't know can you do that? I mean, because I think you would have to...
A dagger would make here a state with 2 A particles and 1 B particle.
Yeah, I'm saying like look at the terms in the Hamiltonian though. I think you'd either have to start with an A or you have to start with a B dagger, right? Isn't that what it sort of says? Right?
Well, the initial state has an A dagger and a B dagger in it.
Yeah, but okay, so yeah, maybe can I point? I don't know, but so I'm saying like you have this times this times this in that order, right? And so the first thing that you choose either has to be an A or a B dagger. So I don't think that we can have an A dagger come first, then an A. So you could have an A and then an A dagger, but you couldn't have an A dagger then an A, right?
Yeah.
I don't know if that's the case or not.
Right, so it would be... You're right. If we normal order the Hamiltonian density, which is what one normally would do, then the A dagger would be to the left, and the A would be to the right, and so this A would wind up having to annihilate this one. All right, so that was a bit of a digression. But, of course, it's important to answer questions. So, in particular, when we set this up this way, you see, what we can have is that A on a state of charge Q gives us a state of charge Q minus 1, and B on a state of charge Q gives us a state of charge Q plus 1. And so if Q is a charge operator, then Q phi of x will be minus Q phi of x, because what we'll have here is that Q with A of P and S will be minus Q A of P and S, and Q of B dagger of P and S will also be minus Q B dagger of P and S. And we'll also have Q with phi dagger of X will be Q phi dagger of X. And so what this means is that if you have, say, a Hamiltonian density that involves something like phi dagger phi, then Q of H of X would be it would be Q phi dagger phi plus phi dagger Q phi, and so this gives you, the first one gives you Q phi, and the second one, I'm sorry, Q phi dagger phi, and the second one gives you minus Q phi dagger phi, which is altogether 0. So this means that the Hamiltonian density commutes with the charge, and that's what you want for conservation of charge. So this homework problem, remember, is over here. I'll put it on the classwork page. So this is so this means charge is concerned. Or this would have been using the passive is always a bad idea. Not always, but almost always. You see here I say charge is conserved, but I'm not saying who's conserving it. What I should say is H of X conserves charge. All right, now I'm going to talk about parity and charge conjugation, and just a little bit about time reversal. And here, I'm going to do these things the way I think about them, which is a little different from the way Weinberg thinks about them. And this is one of the rare cases where I like my way better than his way. Or where, to put it differently, where I haven't just adopted his way of doing things. So here's the parity operator. It takes one so that's what parity does. It takes a creation operator of momentum p and turns it into the creation operator of minus p with a possible phase. And in order for the field, that's a linear combination of A1 plus I, A2, to transform simply, we have to have these transform with the same phase. This in particular means that P, AI of P, I being 1 and 2, is eta star AI of minus P. And then the field transforms as, let us say, Tx, P inverse is then eta star B, right, of x0 minus x. So that's the way I think of it. Now, if we do the thing again, we then have p squared phi of t and x. P inverse is eta star p phi of x0 minus x, p inverse, and so this is eta star squared phi of x0 and x. And if we think that p squared is the identity, and I guess we do, because if by parity we mean it's a general coordinate transformation that turns space into minus space, leaving time alone, then we want p squared to be the same as the identity. And so then we would have eta star squared equal to 1, or eta equal to 1, plus or minus 1. So, the way I think of it is, in fact, let me see if I... Well, let me see. I actually skipped something in my notes here. Yeah, let me just do a little more here. So, I've said how the individual AIs go. This means that P, A dagger P inverse, is equal to eta, A dagger of minus P. And it also means that PA of P inverse is eta star A of minus P. So these were the, remember here we're taking the A is A1 plus IA2 over root 2. And we have P dagger of P inverse is then eta P dagger of minus P. And B, of course, P inverse is then eta star of B of minus P. So, yeah.
I'm just a little confused. What exactly is eta?
A phase.
Okay.
And so what I'm saying is, under this parity transformation, we want the annihilation operator to go into itself. The annihilation creation operator is to transform at most by a phase. We don't want the creation operator for a particle to be a linear combination of the creation operator for a particle plus various annihilation creation operators. So, doing that, that requires that A1 and A2 transform the same way. That then means that the field is going to be an integral dqp PA P inverse EBI PX plus P B dagger P inverse e to the minus I PX. So this one, the A goes into eta star. And now the B dagger goes into eta. So the conclusion that I come to is that if we want to think of the complex scalar field as a linear combination of two equally massive emission fields, then what we need is that eta is equal to eta star. In other words, eta is real. This one then says that eta star squared is 1, so eta, this again says eta is plus or minus 1. Yeah.
Oh, so implicit in here, you only wrote the P, A, P inverse around the A's, not around the E to the IPX. But is that just because under parity you have a P and an X and those both get a minus?
Well, this is a linear unitary operator, so it doesn't affect complex numbers.
Okay.
Let me get you a candy. By the way, I hope you guys brush your teeth occasionally.
Professor, why the phase doesn't change into the minus sign since like P inverse gives you A minus P?
That was my same question. It's in that. So yeah, why doesn't it affect the E to the minus IPX? I mean, it would put a minus sign in front of both of them, so it would. Is that what's happening? The P
Oh,
and the X are both
actually,
getting minus signs?
you guys are bringing up a very important point here. Yes, you're absolutely right, and it's something that I that I expressed here, but didn't mention. You see. All right. So the way I'm thinking of it is like this, but this is A of minus P, and this is B dagger of minus P, minus P vector, okay? But then we can replace, this is an integral over spatial momenta. We can replace P by minus P. This becomes eta star A of P now, e to the I P0 X0, well, minus P0 X0, and now minus P vector dot X vector. And this one is eta B dagger of P, and then this is e to the minus I plus I P0 X0, and we have 1, 2 minus signs plus I P vector dot X vector. So in other words, this is eta star phi of X0 minus X. So the flip of the space due to parity. In other words, parity is basically you flip space and leave time alone. And the way that happens in the way I'm doing things here is that on the creation and annihilation operators, you flip 3 momentum. And after you flip 3 momentum, you have a funny looking field. And so you then flip 3 momentum again, and that means that the 3 momentum changes here, and the minus sign goes to the 3 momentum, the spatial part of the position of the coordinates, and that just means that this is eta star, or eta, since eta has to be real, phi of X0 and minus X. I put this on the web page. Now what Weinberg does is different. He has taken the view in this book that the particles are fundamental and the fields are secondary, which is a very physical point of view. And so what he does is he says that he wants, he does not look at the individual fields. He just says that he's got a complex scalar field with an annihilation. He starts out with the field being a complex scalar field, an A and a B dagger. Then he says that A and B can transform in such a way that there's let's see, so in Weinberg's way, and P dagger, well, of minus P. So Weinberg does this. Did I have that right? No, I don't have that right. No, I didn't have that right. It's funny. Now I'm just wondering whether something's inconsistent here. I think he has eta. Yeah, he has eta star here. And anyway, he does not require eta to be real unless the field is Hermitian. In any event, all right, let's do things my way for the moment here. Suppose the field actually is Hermitian, so we only have one, we just have A, we don't have A1 and A2. In that case, the field, in that case, the field, well, eta, well, already I've got eta as plus or minus 1, period. And consequently, if we have a state of a particle and its antiparticle, the parity has to be positive for a particle and an antiparticle. Let me show you what the state would look like, actually. It would be a state AB like this, integral dqp, some function of p vector squared, and then A dagger of P, B dagger of P on the vacuum. And if you act on that with P, then this is dqp f of P vector squared. This would be A dagger minus P, B dagger minus P on the vacuum. And all right, so in my book, eta is plus or minus 1, but that would be plus or minus 1 squared, and so it's equal to plus 1, and then you can flip the spatial part of the momentum, and so you get back to just dqp f of P vector squared, A dagger P, B dagger P on the vacuum. So that's a particle-antiparticle state, then has even parity here. So the point is here that, where am I? The creation operators go with eta. The antiparticle ones also go with eta, but eta squared is 1, so it's the square of plus or minus 1. That's the way I'm doing it. Weinberg has a somewhat more, he allows more general phases and, okay, let me do quickly charge conjugation, and I'm going to do it. By the way, I can make an extra credit homework if you want. Improve what I'm doing. In other words, for example, say why is Weinberg's better, or how to make them a little more equivalent or whatever. I played with this late last night for a while, and it seemed to me that his way is perfectly fine, of course, if you just focus on the particles and the antiparticles, the complex scale of fields, and don't say that your fields are linear combinations of, complex linear combinations of emission fields. I think if you do say that they're complex linear combinations of emission fields, I think you've got to do it the way I've done it, but if you have a better way than the way I've done it, let me know. That's extra credit, but I don't think this is the most important thing to work on. All right, for the charge conjugation operators, again, from my point of view, looks like this. Some phase C, in fact, I'm going to just oh my goodness, why did I flip the momentum? All right, that's because I moused things in from the Parity exposition and didn't change the momentum. Well, you don't change the momentum if you're doing charge conjugation. And actually, I've got, all right, I don't understand why this is this way, because I thought I fixed this. Okay, what you obviously want to do under charge conjugation is go from A to B. So A is A1 plus IA2, B is A1 minus IA2. So, oh, all right, I do have this minus sign. I didn't see the minus sign. Okay, so this is correct. No. 1 plus sign, C, A2 dagger. Okay, so that's the way things have to go, in my view, for charge conjugation. The two fields transform slightly differently. Same phase, but an overall minus sign. This means that C charge conjugation, in other words, a dagger of P, C inverse is C B dagger of P, and C A of, well, let me just do B dagger of P. C inverse is C. Boy, there are an awful lot of typos. So A dagger and B dagger go into each other under charge conjugation with the same phase, and C inverse is C star A, and CB, C inverse is C star B. And so the field C inverse is an integral. The A's changed by C star, the B daggers by C. So if we want things to be C star B dagger plus C A, no, I've screwed this up again. C A, this is right. Okay, so let's C star B. Well, that, we don't want that. Goodness, that was. We want the field to go into a multiple of itself. A multiple of the adjoint of the field. That's what we want. Sorry. All right, look, I tell you what. Obviously, the number of typos and minor signs here is a little excessive. I'm going to do charge conjugation next, what is today, Thursday?
Yeah.
All right. Next Tuesday, I'll start here. Let me go to something else that I was going to talk about. That's one thing that's more important. Well, let me do something that I've been meaning to show you in several lectures, and it is totally different from one, not totally, but somewhat, it's not in Weinberg's book at all, as far as I know. So as I said, the connection between spin and statistics was established, Weinberg established it for spin 0 in this section that we were almost finished covering. But now, suppose we just look at how fields transform. Remember how fields transform under rotations. Let me get a... So under rotations, we have a. So I'm following now the notation of chapter 10 of the online notes, which is a PDF on the class webpage. So U of R, psi sub s of x, U inverse of R. This is just rotations. And this will be dj of s prime of R inverse psi s prime R of x. So that's how fields transform under rotations. And now I want to consider states AM that are eigenstates and BM that are eigenstates of J3. And the same thing for B.
Is J3 one of the generators of SO3?
Hmm?
Is J3 one of the generators of SO3?
Right, these are the generators of the rotation group. Okay. Now, if suppose U and B are two space-time points that are space-like, then one can go to a Lorentz frame in which U is equal to Tx00 and V is equal to T minus x00. And now let's specify, let's make this U more specific. Let's say U is a rotation, say a right-handed rotation by pi. So this U is e to the minus I pi J3. And so U on AM is going to be e to the minus I pi m AM, which is to say minus 1 to the m AM. And the same thing for B. In fact, I'm going to have B on the other side. So BM U inverse is going to be BM e to the I m pi. And in fact, if we just, which is to say BM minus 1 to the m, and so essentially one is the adjoint of the other. Yeah.
Yeah, what are A and B?
A and B are just describe all the other possible quantum numbers in the state.
Okay.
So I'm trying, I would like,
So why
this is sort of a poor man's, me being the poor man,
Okay.
a poor man's spin and statistics theorem. It establishes the connection between rotation and between spin and statistics. It suggests that the connection between the behavior of fields under rotations is related to what statistics they have to obey, but it isn't a complete proof. And the reason it isn't a complete proof is that I've got to use these funny states, these eigenstates, as opposed to just totally arbitrary states. I think that's the only thing that's actually a limit in the derivation. Okay, now let's see how the field transforms. So U, this particular U, psi s of t and x, U inverse is now dj s prime of R inverse psi s prime, and now it's t and minus x because we've rotated. We're in this particular frame, we rotate x to minus x. So it's a rotation about the z-axis, and so x goes into minus x, y into minus y, but I'm not paying any attention to y. And this is then e to the I pi s psi s of t and minus x. All right, so now let's look at Bm psi s of t and x, psi s, yeah, I think here's another limitation. I'm using the same s. I don't think that's necessary. I'm also using the same m. I don't really think that's necessary either. But anyway, what happens to this? Well, we can rewrite this as Bm U inverse U psi s of t and x, U inverse U psi s prime of t and minus x, U inverse U am. Okay. So now we've got the Bm under U inverse is minus 1 to the m. U on am is minus 1 to the m. So altogether this is minus 1 to the 2m, which is, well, let's see what m is. Minus 1 to the 2m and then this U psi s U inverse gives us e to the I pi s. So this is e to the I pi s Bm psi s of t minus x, and now this will be psi s prime tx, and again e to the I pi s prime. Or did I take the same s? I'm using the same s, so this is not s prime. Okay, so these states, oh wait a second, there's a subtlety here that I did not the e to the im pi's actually cancel. So let me get this straight. U on that is e to the minus I pi m. Bm U inverse is e to the im pi. So these actually cancel.
You can also see it that you have negative 1 to the 2n.
And in fact,
Oh, but I guess it should be
let me not use that. So let me change this. Let's get rid of that. Instead, what happens is this phase factor and that phase factor cancel. So we get rid of this term. And so now what we have is e to the 2I pi s. Fine. Make it simple. So now what do we have? What's the conclusion? What's the conclusion? The conclusion is that at least between the states AM and BM, all right, there's an AM here that I left out. If S is an integer, this is just 1. And that tells you that the fields at space-like separations and the same S commute. On the other hand, if S is a half odd integer, if S is a half, 3 halves, 5 halves, 7 halves, then this is equal to e to the I pi, e to the 3I pi, and so forth. It's an odd number of I pi's. You have a minus sign here. That means that the anti-commutator vanishes. So this tells you that the commutator vanishes at least between these states, AM and BM. The A's are totally arbitrary as long as they're not spin indices. Okay, so this says that this is part of the reason why the behavior of fields under rotations entails how they behave under what their statistics are, whether they're bosons or fermions. It's not a total proof because at least in this description here, I had the m's equal on the two sides. The state to the left and the state to the right have the same angular momentum in the z direction, and I chose S and S prime to be the same. So it would be nice. So a super extra credit homework problem is to prove this argument. But as I said, don't knock yourself out on it.
So what lets you write the dj ss prime are inverses just e to the I pi s? I missed that step.
Oh, because this is the rotation about the z-axis, the representation of the rotation. It's really a representation of the rotation group that's it would be of pi about the 3 axis. So it's e to the it's e to the I j3, e to the I pi j3, or e to the minus I pi j3, or actually e to the I pi j3. So because it's R inverse. And then the representation of that is just e to the I pi s. It's a matrix, right?
It's the normal.
It's a matrix. It's a matrix, but when it hits this S prime, it's diagonal, so we get S. The S that's the S on the other side.
Okay.
Yeah.
Yeah, so, whenever you say like spin statistics, I would expect that you would make some connection to the J in the representation that you've chosen.
Well, yeah.
So,
The S values, I mean, that's ordinary quantum mechanics. The representations of the rotation group are such that if you have a spin J representation of the rotation group, the values of S go from minus J to plus J in integer steps. That's just the way the rotation group works.
Sure.
So it goes from minus a half to plus a half in
Okay.
the simplest
Yeah,
case.
so S is always either going to be half integer or integer. You're never going to have a case where you might have S sometimes being integer, sometimes being half integer.
Right,
Yeah.
yeah.
I see.
Anyway, this is, I'm just taking this out of part of the online notes. Okay, so
Is that from your book?
you can see it, huh?
Is that from your book?
Yeah. So I think it makes clear intuitively why there's this connection, but it's not a rigorous mathematical proof for the reasons I just mentioned, and possibly other reasons. Okay, I think we're done. We're 5 minutes over.